All right, so now what we're going to do is let's investigate what's going on with 2x2 matrices and a 3x3 matrix when we do this row operation. So let's say we have a 2x2 or a 3x3 matrix T. We're going to do this row operation on one of the two of the rows. So we're going to take K times one row plus R another row, okay? And that's going to give us T hat as another matrix, resulting matrix. So then the question then becomes, are the determinants the same? Well, let's do this with a 2x2 matrix and see what that gives us. So here's our matrix, and of course with our operation, our resulting matrix will be what? Well, we're going to take K times, let's say, row 1 and add it to row 2. So this will be unchanged, and so what's going to happen? We're going to get K times A plus C, and then we'll have K times B plus D. Okay, so that's our new matrix. Now, what happens if we take the determinant of that? Well, we know the determinant of this side, right? The determinant of this, so we'll do T of this and right? And so are these equal? Let's find out. So this is going to be equal to AD minus CB. What happens here? We get A times KB plus D minus B times KA plus C. And what do we get here? Let's distribute. We get AKB plus AD minus BKA plus, or minus, because we're distributing, minus BC. But notice here, this product is the same as this product, but they have opposite signs. So this minus this, and look at that, we get the same thing, AD minus BC. So they're the same. Not bad. Okay, that's a good sign. All right, let's do the 3x3 case. See if we get the same thing. Okay, so now let's just do the 3x3 case. So we got A, B, C, D, E, F, G, H, I. Now, if we do the transformation, what do we get? And I'm gonna make this a little bigger just in case. So again, it doesn't matter which rows we use, but let's just do two of the rows. In fact, it doesn't matter which two rows. Let's do the first and second row again. So let's say we've got A, B, and C, and then this will become KA plus D, KB plus E, and then KC plus F, and of course this is unchanged, so we get G, H, and I. Okay, now let's look at these formulas. The formula over here is, I'm going to write it over here. So AEI plus BFG plus CDH minus, how do I want to do this? Minus BFG minus, oh, hold on. Minus right? So that was from before. Yep, that's correct. So now let's see if we get the same thing over on this side. So in this case here, we follow the pattern. It'll be A times this times that plus that plus okay, and now minus that minus minus that. Okay. Yeah, that's right. So now let's see if we distribute, if we get the same thing. I don't want to erase this, so I'm going to write it up here. See if we can get some cancellations like we did before. Oops. So we'll get A, KB, oh, hold on. A, KBI plus AEI plus BKEG plus BFG. Notice these three terms are already matching up with these. It's a good sign. Plus CKAH plus CDH. So my guess as I'm going through this is these four letter terms are going to fall out. They should, right? If they're the same, all the four letter terms should fall out. So now we've done the three positives. Let's do the negatives now. So we get minus HKEA minus HFA minus IKAB minus IDB minus GKBE minus GEC. All right, now let's look. So we got AKBI here, AKBI here. Those will cancel. We've got BKEG here. We've got BKEG here. Those will cancel. CKAH. Oh, I'm missing one. Hold on. CKAH. Oh, hold on a second. This is a C. That's why my handwriting was sloppy. There we go. So that means right there. Okay. So CKAH, CKAH. So these cancel. And finally, what was it? Oh, that was it. Yep, those three. So those six, I mean, cancel. So what are we left with? We're left with AEI, AEI, BFG, BFG, CDH, CDH minus IDH, wait a minute. Did I mess up again? Where? Oh, because that's right. So HKC HFA. Yeah, that's that. Okay. So HFA. Did I mess up this one? Hold on a second. Okay, right. So IDB, HFA, HFA. Yeah, okay, I got them all. Okay, yeah. I don't know what I was looking at, but yeah, they're all there. So it worked out, they're equal. Nice. Okay, so now after doing these two, it seems like there's some hope, right? It seems like it's working. Now, perhaps if we work out like the 4x4 determinant model formula and tested, that we might have found that it is affected by row combinations. Now, keep in mind this is an exploration, and we don't have to have we don't have all the facts yet, but so far so good. Okay. So where do we go from here? Now what we're going to do is we're going to compare the determinant with row swaps. Okay? And here we're going to hit a snag. Okay, and let's just go through one. Okay, now, over here, the determinant is going to be right? Over here, they're not the same, not necessarily. Okay? Subtraction is not commutative, so there is a problem there. Now, if we do the same thing with the 3x3, it will also run into a problem. It will not give the same determinant. It will give a sign change, just like we see a sign change here. So row swaps appear in this experiment to change the sign of a determinant. Okay, so so basically there's something to take away from it. So we learned something. Okay. Now our hope is to decide non-singularity by considering only whether the formula gives 0. Not by considering the sign. So this isn't a big deal, or it has a potential of being a big deal, but hopefully it won't be. Okay? Because really it depends on whether it's equal to 0 or not. Whether it's positive or negative doesn't matter. Okay, so instead of expecting determinant formulas to be entirely unaffected by row operations, we're going to modify our plan so that on a swap, they will change sign. And then finally, let's do scalar multiplication. Okay, so what happens here? Let's do, again, our determinant. I don't know why I erased that, but anyway. So AD minus BC. And then over here, we have AKD minus BKC, which is actually equal to Which now look at this. All it did was it takes the determinant of the original matrix and scales it by k. But it doesn't change the fact that if this is 0, it's still 0, whether you multiply it by a scalar or not. And of course, if we investigate the 3 by 3 case, what we'll find out is we'll find out the same thing. That you can actually factor out the k, so the whole determinant gets multiplied by k.